Welcome to Group Theory. Today, we are going to explore a fascinating and powerful concept called factor groups. If you have ever wanted to simplify a complex mathematical system into something much easier to handle, you are in the right place. Let us dive in and discover how we can zoom out on mathematics. Let us start with a simple analogy. Imagine you have a massive pile of laundry and you want to organize it. Instead of looking at every single shirt and sock individually, you decide to group them by color into a darks pile, a lights pile, and a colors pile. You have just created a factor group of your laundry. In mathematics, a factor group, which is sometimes called a quotient group, takes a very large, complicated group of elements and clumps them together into smaller, manageable categories. We treat these entire clumps as if they were single brand new elements, zooming out so far that a whole cluster looks like just one single dot. Now that we understand the intuitive idea, let us look at the mathematical building blocks required to make this happen. To build a factor group, we start with a mean group, which we will call G. Inside this group, we need a special kind of subcollection called a normal subgroup, which we will call H. We use this normal subgroup as our glue to stick elements of G together into clumps. These clumps are mathematically called cosets, which are just shifted copies of the subgroup. The factor group, written as G over H, is the brand new group where the elements are actually these entire cosets, acting like buckets that we can add or multiply. This brings us to an important question. How do we actually multiply or add these buckets together? The rule is surprisingly natural, and it comes directly from how the elements interact inside the original group. To multiply the bucket AH and the bucket BH, we just take their representative elements, A and B. We multiply them together in the original group to get A times B, and then find the bucket that contains this new element. This new bucket is ABH. The variables A and B represent individual elements from our original group, while H represents the normal subgroup. As A and B change, we are simply picking different buckets to combine. Before we move on to an example, we must ask a critical question. Why must H be a normal subgroup for this bucket multiplication to work? The equation shown here is the exact definition of a normal subgroup. It guarantees that shifting the subgroup by an element A from the left side gives the exact same bucket as shifting it from the right side. If each were not normal, our bucket multiplication rule would completely break down. Imagine picking a different shirt to represent the darks pile, and suddenly the result of combining piles changes. Normality guarantees that no matter which specific item we pick from a bucket to represent it, the final combined bucket will always be exactly the same. Let us see this with a concrete visual to really lock in the concept. The diagram you are looking at visually summarizes exactly what we just discussed. The large oval represents the original complicated group G. By dividing it into equal-sized rectangular blocks, we have created the factor group. You can see the normal subgroup H on the left and the shifted cosets next to it. The arrows prove that when you combine an item A from one block with an item B from another block, you always land safely inside a specific, predictable third block labeled ABH. Now that we have a strong visual understanding, let us apply this to our first concrete example, the integers modulo 3. Let the main group G be the set of all integers under addition. This is an infinite, massive group. Let the normal subgroup H be all multiples of 3, which we write mathematically as 3Z. Our goal is to find the factor group Z over 3Z and show exactly how its elements add together. We will do this by figuring out exactly how many distinct buckets we can form by shifting our subgroup. Let us start setting up our buckets. Since we are using addition instead of multiplication, our cosets will look like A plus H. First, we define our normal subgroup, which acts as the 0 bucket. It contains all numbers that leave a remainder of exactly 0 when divided by 3, like -3, 0, and 3. We can think of this as our home base. Next, we create a brand new bucket by adding the number 1 to every single element inside H. This forms a completely separate, non-overlapping list of numbers, representing all integers that leave a remainder of 1. Continuing our process, we create another bucket by adding the number 2 to every element in our home base H. This specific bucket captures all numbers that leave a remainder of 2 when divided by 3, like -1, 2, and 5. But look what happens if we try to make a fourth bucket by adding the number 3. We get the exact same list of numbers as our original subgroup H. Because of this looping behavior, we do not get a new bucket. Therefore, we only have 3 distinct buckets in our entire factor group: the 0 bucket, the 1 bucket, and the 2 bucket. Finally, we must test our addition rule to see how these buckets interact with each other. We want to add the remainder 1 bucket to the remainder 2 bucket. The rule says we do this by simply adding their representative numbers, 1 and 2, which gives us 3. So the mathematical result is the bucket shifted by 3. But as we just saw a moment ago, shifting by 3 gives us the exact same bucket as our starting subgroup, H. This makes perfect physical sense. If you have 1 extra item and 2 extra items, they combine to make a full group of 3, leaving 0 extra items behind. Let us look at a second, more geometric example to see how factor groups handle physical symmetries. Let G be the group of symmetries of a square, which mathematicians call D4. This group has a total of 8 elements, 4 rotations and 4 reflections. Let H be the subgroup containing only the rotations, which has exactly 4 elements. We want to find the factor group D4 over H and understand what it represents physically. We will do this by grouping the 8 total symmetries into buckets using the rotations as our base bucket. We begin by calculating exactly how many buckets we get in total. The vertical bars around the group name mean we are measuring the size or order of the group. The total number of elements in our main group is 8. Meaning we start with 8 distinct physical movements of the square. The size of our normal subgroup is 4, containing only the pure rotational movements. We are going to use this subgroup as our primary bucket. Everything inside this bucket will be treated as if it were just the identity element, meaning no change has occurred. To find the total number of buckets in our factor group, we divide the total number of elements by the number of elements in each bucket. 8 divided by 4 tells us there are exactly 2 buckets in the new factor group. This is a massive simplification. We have reduced an 8-element system down to a 2-element system. The 2 buckets are the rotation bucket and the reflection bucket, represented by RH. Our factor group has perfectly separated the spinning motions from the flipping motions. We now treat any rotation as one object and any reflection as a second object. Let us see what happens when we multiply the reflection bucket by itself. We take a reflection from the first bucket and a reflection from the second bucket and perform them one after the other. The rule for factor groups says we just multiply the representatives together, giving us R squared H. Doing any reflection twice in a row brings the square back to its original starting position, which is the identity element E. Since the identity element belongs in the rotation bucket, combining 2 reflections always results in a rotation. We have successfully zoomed out from 8 complex symmetries to a simple system that just tracks whether the square is flipped or not. Now that we have calculated factor groups, why do they actually matter? They are the ultimate mathematical simplification tool. In computer science and cryptography, factor groups are used to break down massive, computationally impossible numbers into smaller, modular arithmetic systems that computers can handle instantly. This is the exact math that secures your credit card online. In physics, factor groups help scientists ignore irrelevant data, For example, a physicist studying a crystal can use a factor group to factor out the infinite repeating grid and focus only on the unique behavior inside a single microscopic cell. Let us review the key takeaways from our journey today. A factor group is a powerful method of simplifying a large group by clumping its elements into equal-sized buckets called cosets. We use a normal subgroup as the template for these buckets to ensure that the math remains perfectly consistent. By treating these entire buckets as single elements, we create a smaller, zoomed out version of the original group. You have now covered the full topic and have the tools to ignore microscopic details and focus on the macroscopic structure of any system.